So now that we've discussed where mixed formulations often come from, namely constraint minimization problems, and now that we've talked about the necessary and sufficient conditions for existence and uniqueness of a solution, namely the LBB conditions, it is time that we start talking about how to obtain actual approximations to these solutions by means of a finite element discretization. And the study problem that we'll use is the Stokes problem, written at the top here, where we have already the weak formulation with an A part and a B part. And now we know that the A part corresponds to the minimization problem and the B part corresponds to the constraint, right? Where in this case the constraint is a constraint on the divergence of the flow field being equal to 0. So that's what we saw in the last couple of videos. Up to that point though, we didn't really talk about discretization methods, so we talked about this in a continuum sense, meaning that our function spaces are infinite dimensional, right? So we're talking about an H1 space and L2 space. And now we want to discretize these spaces, so we want to use discrete subsets of these function spaces. And if we do that, then this weak statement can be rewritten in terms of a matrix system of equation, and we get the one on the bottom here, yeah, where naturally the A part of the matrix corresponds, or sorry, the A part of the bilinear form corresponds to this A block in the matrix, and then we have the B parts of the weak form corresponding to these two B blocks, right? So at this point, this is still a symmetric discrete system of equations, symmetric matrix, and that is of course due to the symmetry in the original weak formulation. Now, the issue that we've been discussing, or at least that I've been pointing out already a couple of times now, is that a challenge with problems like these is that the LBB conditions, even if they're satisfied in one case, it doesn't mean that they're also satisfied in another case. And what I mean by that specifically is that we can prove that the Stokes equations are well posed in the sense of the LBB conditions for spaces H1 on the velocities and L2 on the pressures. But even though they're well posed according in those spaces, so the LBB conditions are satisfied with those spaces, that actually does not mean that they're also satisfied for our discrete spaces. And this was different from coercivity. If we could prove coercivity of a bilinear form, then we would also have a well-posed finite element formulation, because then we're simply dealing with subspaces, and coercivity on the complete space also meant coercivity on the subspace. Again, for the LBB conditions, that is not the case. Yeah. So proving it for the infinite dimensional case does not actually mean that we get a stable finite element discretization. Now, clearly that's a problem, and we're going to have to find different ways of trying to determine whether our finite element discretization can be effective. And the first thing that I'll do is I'll actually give you a couple of examples of where finite element discretizations are not effective, and then we'll also see why that is. So I'll actually show you that one of the LBB conditions is not satisfied for these particular spaces, these finite element discretization spaces. And after we've seen two examples of spaces that don't work and talked about the reasons for why they don't work, I'll give you one more example of a space that does work. Now, actually, that's going to be more tricky to understand. So then we'll try to find sort of a rule of thumb that we can adhere to get a first idea of whether a space is going to be effective or not. And afterwards, I'll also try to give a bit of more rigorous analysis and more rigorous computational analysis that you could do to figure out if spaces are suitable or not. Okay, so this the finite element spaces that I'll focus on are going to be these three. I'll start with a discretization that is characterized by this schema. And I'll tell you in a second what that means. The second one that we'll look into are going to be elements that are characterized by these drawings. And the last one is going to be a mesh with these kind of elements. Okay, so what do these drawings mean? And I think we already saw these drawings a couple of times in this class. So let's try to understand what they're actually trying to tell us. So the idea here is that we would develop a certain mesh. So let's assume that our domain is actually just a square. And now we're going to mesh this square with elements of these shapes, right? So on the left one I actually have triangular elements. The second one and the third one are square elements. So in all cases though, I can get a mesh of these squares, where in the first case we might still subdivide everything by triangles. Okay, I think up to that it should be relatively clear. Oh, sorry, on my third drawing I'm forgetting to add the open circles. That would look like this. Okay, so they just show the element shapes. So what do these open and closed circles mean? Well, the closed circles are going to be our degrees of freedom for the velocity. And the open circles are going to be the degrees of freedom for the pressure. So the one on the left, what that is saying is we're going to take on each corner of our triangles, we're going to add one node for our velocity degree of freedom field. Whereas for each triangle at the center, we're going to introduce 1 degree of freedom for pressure. So naturally that means that the pressure is going to be discontinuous from element to element in the first case and the second case, right? There's only 1 degree of freedom inside of an element, so that's going to be a constant value at that point. If we only have 1 degree of freedom to represent a field, then that's going to be a constant value. So it's going to be constant in each element, and then from element to element it might jump, right? So we have a discontinuous field to approximate the pressure. Now, is that okay? Well, actually, yes, it is, because our pressure variable lives in the L2 space, right? So we had very little restriction on the smoothness of our solution field, of our approximation space. So discontinuous functions are actually in L2. So we're allowed to make use of an approximation method that has discontinuities. Yeah? So that's the case for the first element and for the second element, right? In the second element, we also have squares where from square to square our pressure may be discontinuous, and in each square it's going to be a constant. Yeah? Now the same thing for the velocities. They can actually be continuous in the first, the second and the third element because, well, we only drew these degrees of freedom in the nodes. All these elements share these nodes, so they can have the same velocity on each one of the nodes, and then we get linear interpolation across the edges. So that means that we can have a continuous field for the velocity. We also need a continuous field for the velocity because the velocity is in h1. h1 required us to be able to take first derivatives without any problems. So we're not allowed to have discontinuous approximations for the velocity. And indeed, we only have continuous approximations. And in the third element, we have more degrees of freedom for the velocities. That means that we have a quadratic field for our velocities, whereas we have a linear P1 field for our pressures. So let's also write that down. The other way that we write these spaces is P1, P0. So what does that mean? This is going to be a tessellation, a distribution of a geometry in terms of triangles with first order basis functions for the velocities and zeroth order basis functions for the pressures, right? The first order means linears, so these are linear elements, linear triangles, and P0 means that there's just constants per triangle. Now the second one is going to be Q1, Q0. So that means that we have first order basis functions on squares. Now, why do we make the distinction between P and Q? That is because to be truly linear, we're only allowed to have 3 degrees of freedom on a triangle. That defines a linear plane, right? The plane is really only defined by 3 values. So on a square, we're never able with 4 degrees of freedom to define a plane. And indeed, actually, a square is the approximation with polynomials on a square. They're not truly linear. There's some curvature in that. So that new space is what we then call a Q. And we also have Q0. It's still constants, right? So technically, actually, Q0 would be the same thing as P0 in the sense that the space spanned by 0th order polynomials, it doesn't matter if that's on a square or a triangle, it's just going to be a constant. Yeah. So, but nevertheless, I'll stick with Q for this one. And the last one is going to be Q2, Q1. Right? So we have quadratic basis functions on square domains for the velocities, and we have linear basis functions on square domains for the pressures. Okay, so these are 3 different ways of trying to discretize our spaces H1 and L2 for our velocities and our pressures. In each case, we would get a finite discretization system matrix that looks like the one that we have right here with the A and the B transpose. Because in each case we have a compatible, or sorry, a consistent discretization of this weak statement with discretization spaces that are subspaces of the relevant spaces. So in each case we get the same general shape and outline of our matrix. Now naturally the number of degrees of freedoms that we would have in our solution vector is going to be different, and also the actual values in each one of these matrices is going to be different, right? But the general outline of this matrix would always look the same. Okay, so then what were our conditions for solvability of this matrix? Well, that became the LBB conditions. And the first LBB condition said something about our bilinear form A, or equivalently the matrix A, namely that this was sort of coercive, but only in a certain subspace. Now, if you're again confused about that, then go back to the video on that topic. For what I want to point out here, though, is that this is a coercivity property, and in principle we're quite happy with coercivity properties. They don't tend to give us a lot of issues. And secondly, this condition was required to obtain a velocity solution, right? So the first condition kind of corresponded to being able to obtain a velocity field. So the second condition was an inf subcondition on the second bilinear form, the B bilinear form. And we did some analysis, and then we found that there was actually a quite strong relation to linear algebra for the matrix B, and namely that B had to be full rank, and it had to be a column matrix in the sense that its number of rows was larger than its number of columns. So it has it's a standing matrix. So those were the linear algebra equivalents of the inf subconditions for the weak statement. And those conditions were important for finding a pressure solution after we had already found a velocity solution. Right? So the first LBB condition guarantees the existence of some velocity field that satisfies the equations. And the second LBB condition then guaranteed the existence of also a pressure field, given already that velocity field. So why am I pointing that out? Well, that means that the condition that we're struggling with, the second LBB condition, that was the inf subcondition. That condition concerns solving the system of equations B, P, V is equal to, and then we have here R. So that's the equation that we get after we already obtain a velocity and we're trying to solve for a pressure. So then we have L V minus A U, V for all v, right? So now we're trying to obtain a pressure after we already obtained our velocity. So then these are the leftover systems of equations. And our if subcondition said something about the full rankness of this matrix B. So what does that explicitly mean? Well, that means that for any possible vector P here, vector of coefficients P, if I multiply B by P, I will always get a different result if my P is different. Yeah, that means that that's the result of it being full ranked. Full ranked again was that all of the columns were linearly independent. So then if I take an arbitrary P and I multiply each one of the columns with a certain coefficient, then that's going to be a linear combination of these columns. So for each different P, given that the columns are linearly independent, we would get a different output. So how can we test if that condition holds for a certain discretization, any one of these elements below? Well, it's actually rather difficult to test that that is true, but proving that it is not true only requires a single counterexample. So the counterexamples that we will give are going to be examples where I can find a certain pressure. I'll give two different types actually, because I think that's instructive. One of them is going to be that I'll show that for a given pressure, I actually do not change my result after I multiply B with P. So P is going to be then independent of this addition, this one pressure field, and that's called a spurious oscillation. That's a zero energy mode. So that means that this operation is unaware of my addition of this arbitrary pressure field, right? And that then illustrates that the matrix B is not full rank, which means that the inf subconditions are not satisfied. And the second example that I'll give is that we actually get a zero value out of our operation BPV. Which also says that the inf sub is not larger than a positive constant. Yeah, so there's two different examples that I'll give you where we can, by a counterexample, show that the inf sub conditions are not satisfied. Okay, and I think that the first one that I'll do is also actually the simplest one, and that's going to be the one all the way on the left here. So we're going to start with element example number 1 here. And the procedure that we'll take is that again we'll assume a square domain, and we assume that we have filled this square with equidistant set of these elements. Etc. And then we will try to perform the integration indicated by that operation, by that bilinear form. Right? So B, I'll repeat it, B PV was defined as the integral over our complete domain omega times the pressure times the divergence of the velocity. And okay, let me also, for clarification, just one more time write down what the inf subconditions then were. These were that the infimum over our P in, now we have this discrete space, right? So let me just write this as, I'll write this QH of the supremum of V. So let me actually specifically emphasize here that we're dealing with the discrete case now. So VH also. In the space VH of B P V divided by the norms. Oh, sorry. and this should be an L2 norm, and this should be an H1 norm. That's going to be larger than or equal to a constant gamma, which is larger than 0, right? A positive constant. So that's the condition that we're trying to prove, or in this case actually disprove. I'll show that this does not hold. So let's try and perform this operation, and let's actually specifically try the upper part of this operation. So I'm going to evaluate B of P, V on this square domain with these elements. Now, and actually that's not quite so difficult as it may sound. It's something that we can actually write out relatively easily. So first of all, we're going to subdivide this domain omega into all the element domains. So that then gives me that B, P, V is going to be the sum over all these elements. And I'll write that sum as sum over K. Yeah, so each one of my elements I'll denote K. As the integral of K of our one single element of pH times divergence of VH inside of that element. Now if I then take a look at our elements, then we find, or at the elements that we're considering, then we find that the pressures are constant inside of each element, right? So inside of each one of these operations, I can actually pull the pressure out of my integration. So that means that this is the same thing as the sum over my elements times the pressure. Let me also add a subscript here to distinguish between the different variables in each one of the elements. So I'll get Ki. No, I don't like the way that I'm writing this. Actually, it doesn't matter. Okay, Pi, integral of the divergence of V. So, what is this? This is already telling me something. In my constraint equation, so the lower equation here, this is saying that B, Q, U is going to be equal to 0 for all choices of Q. And in our case, we're currently considering the discrete solution space for Q. So let's try and interpret that condition from what we've just written down. So in each one element, I have one choice of P here. Now, so let me actually change my variables now into the ones of Q and U. So B, Q, U is going to be equal to the sum over all the elements of Q times the integral of Ki times the divergence of V. And our constraint equation is saying that this has to be equal to 0 for all choices of Q in our discrete space QH. So that means that I can individually on each element choose any Q. So in each one of the elements I can start fluctuating my test function Q, and this still has to be 0. Yeah, so one thing that I could do is I could set Q equals 0 everywhere except on one element, and that would give me that on that element QHI times the divergence of VH on this particular element is going to be equal to 0 for all QHI. Now, yeah, that's a real number. So then I'm singling out a single element. So naturally, if this has to be true for any arbitrary choice of Q, well then that means that this thing has to be 0 by itself. So then let's try and look at this distribution of elements going all the way from the bottom left here. So I'm going to zoom into the bottom left. where I still have the velocity degrees of freedom in each one of the corners. So apparently my constraint equation is telling me that the divergence of my velocity field is going to be equal to 0 in each element individually. So let's focus on this one element here. Now, the only degree of freedom that I have left for my velocity field is the one over here, right? These ones are set, so I'm assuming certain boundary conditions. I'm assuming that I have Dirichlet boundary conditions on the boundary, right? So essentially I've removed this degree of freedom from my space. I've set that to 0. So at this node, the one left over node, I have a velocity to the right, and I have a velocity to above, or one of the x-axis, one of the y-axis. The one on the y-axis is never going to give me a divergence-free result, and the one on the x-axis actually it doesn't have any impact on the divergence, right? It has to do with the size of a certain triangle, the volume given a base and a height is fixed. Yeah, so arbitrary doesn't matter where exactly on that height I put my node. The total volume of that triangle is always going to be the same, whether it's this or this or this. Each one of these is going to have the same volume. Yeah, so my x degree of freedom is still free. Any choice of Vx is going to satisfy this result, this requirement, but the y direction does not, right? So I'm actually completely constrained in Vy, in the sense that for this particular element we can already conclude that Vy has to be equal to 0. Again, for this element, on this node. Right? Vy is equal to 0, and Vx is still free. Now if we then actually look at this element, I can make the same drawing, and I'm going to say that actually my degree of freedom in y is still free, because any choice of Vy is still going to be divergence free. The area of the triangle is going to remain the same. But my velocity in x is constrained. I'm not allowed to move this node to the right or the left, because that will give me a different volume of my element and hence a non-divergence free velocity field. So according to this element, I actually have that Vx has to be equal to 0. Yes, so the only solution that we're permitting here is a solution where both Vy and Vx are equal to 0. So this node is fixed. It's not allowed to move. So then after that I can go one element to the right, and I can start making the same claims on this node. Well, from the perspective of the lower element, I'm only allowed to move it along the x direction, but from the perspective of this element, given that this node was set to 0, I'm only allowed to move this to the top and the bottom. And as a result, I'm not allowed to move that node everywhere. So also this node is going to be fixed. And in this manner, I can traverse the entire mesh, and I actually find that the only solution that I'll permit is a solution where we have a completely zero velocity field. And that's what we call complete mesh locking. That's a very extreme situation of mesh locking, where we have this on the complete domain. And this actually occurs in relevant simulations as well. We talked about this problem before, the lid-driven cavity problem, where we tried to solve the Stokes equation on a square where we have indeed 0 boundary conditions all the way on the bottom and a unit boundary condition at the top. So the element type that we're then interested in, that we're currently considering, is the one all the way on the right, where we have discontinuous pressures from triangle to triangle. And indeed what we see is that we get a completely zero velocity field. Now this is the velocity field, it's completely zero. Well, naturally, except for at the top nodes there, they have a fixed value. Yeah, so clearly these are not very useful elements for these kind of computations. They're completely locked, they give you a completely wrong solution field, and that's not what we're looking for. Okay, so this is the first example of a little bit of analysis that we can go through to make already claims on how poorly our finite element methods may behave for the Stokes problem. Now, one thing that we saw is that this actually depends a little bit on our choice of domain and on our choice of boundary conditions, right? I'm specifically focusing here on a square domain where we have 0 boundary conditions on the sides, so that we can make this traversal here. Now, this indeed means that for a different domain and with different boundary conditions, I might actually get good results. And that also illustrates how sensitive these methods or these formulations are to your choice of spaces, right? And naturally what we want to have is a space that works for any kind of domain and any kind of boundary conditions, right? So we wouldn't want to use spaces that start to show these kind of problems in particular cases. Maybe in any corner where you have 0 velocities prescribed on part of the edges of the corner, you would get locking, which might also affect then the remaining volume. So I think this was still a relatively straightforward example. The second one is going to be slightly more involved, and that's the one that's also going to have to do with these in subconditions. So I think I'll actually leave that for a second video. Yeah? So I'll get back to that in the next video. Thank you for your attention.